Today we talk about the differentials and the chain rule applied to functions of several variables. At the end of this lesson, you must be able to determine the differential of a function of two or more variables and to determine the derivative of a function of several variables using the chain rule. Okay, let us recall the differential of a single variable function y equal to function of x. Remember, the differential dy is given by f prime of x times dx. So if we are dealing with a multivariable function, such as in the case of z equal to function of xy, how is the differential of dz now obtained? Now, the differential of dz, or the total differential of z, would just be the sum of a differential in x and a differential in y. So the total differential dz would be given by the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. And in the case of having a function w which is dependent on three variables x, y, and z, then its total differential dw will be equal to the sum of the following differentials: the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy plus the partial derivative of f with respect to z times dz. Okay, to apply it to this particular example, consider the function z defined by 5x squared y to the fifth minus 2x plus 4y plus 7. Let us work out the total differential of z. Recall that dz for z function of xy would just be given by the sum of the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. Hence, dz will now be given by this expression where 10xy to the fifth minus 2 is just the partial derivative of z with respect to x, and 25x squared y to the fourth plus 4 is the partial derivative of z with respect to y. Hence, dz is given by the sum of the following products: 10xy to the fifth minus 2 times dx plus 25x squared y to the fourth plus 4 dy, or we can express dz in this given form when you multiply the factors as indicated. Let us look at how we can apply the chain rule to determine the derivative of multivariable functions. So let us consider we have the function z, which is defined by f of xy, where x is function of t as well as y, a function of t. So how is the derivative of z with respect to t determined? Then that will be defined in terms of the sum of the following products: the partial derivative of z with respect to x times the derivative of x with respect to t plus partial derivative of z with respect to y times the derivative of y with respect to t. And that if we are dealing with w, a function of x, y, and z, where x, y, and z are again expressed as functions of the variable t, then the derivative of w with respect to t would just be equal to the partial derivative of w with respect to x times the derivative of x with respect to t plus the partial derivative of w with respect to y times the derivative of y with respect to t plus the partial derivative of w with respect to z times the derivative of z with respect to t. Okay, to illustrate this, let us consider z function defined as the natural log of 2x squared plus y, wherein z is defined equal to the square root of t and y is t raised to the 2/3. Here, whereas for the derivative of z with respect to t. Now, using the chain rule, the derivative of z with respect to t would be given by the product of the partial derivative of z with respect to x multiplied with the derivative of x with respect to t. The second term would account for the partial derivative of z with respect to y times the derivative of y with respect to t. Okay, so that if you will now process this, Then, with z equal to the natural log of 2x squared plus y, its partial derivative with respect to x would be, okay, recall, the derivative of ln u, it's du dx divided by u. So we have there 1 divided by 2x squared plus y, and in the numerator is the partial derivative of 2x squared plus y with respect to x, which is just equal to 4x. Now, if you will differentiate partially the function z with respect to y, then you will have there 1 over 2x squared plus y times the partial derivative of 2x squared plus y with respect to y, which is just equal to 1. So with this, okay, having defined x equal to the square root of t, then the derivative of x with respect to t, this is an ordinary derivative, would equal 1 divided by 2 the square root of t, and that the derivative of y with respect to t on the basis of y defined equal to t to the 2/3, then its derivative would be a 2/3 t to the 2/3 minus 1, or that would give you t to the negative 1/3. Okay, so on this basis, what then is the derivative of z with respect to t? As given here, it will be the partial derivative of z with respect to x, which is now what we obtain here, times the derivative of x with respect to t. The chain rule for partial derivatives. Now let us consider that we have z function of xy, where in turn x and y are functions of u and v. If we want the partial derivative of z with respect to u, then it can be done using the chain rule as follows. We first differentiate z partially with respect to x, and then multiply this with the partial derivative of x with respect to u, plus the product of the partial derivative of z with respect to y times the partial derivative of y with respect to u. And for the partial derivative of z with respect to v, we have it equal to the sum of the following products. The product of the partial derivative of z with respect to x times the partial derivative of x with respect to v, plus the partial derivative of z with respect to y times partial derivative of y with respect to v. And in case we have w a function of three variables x, y, and z, where x, y, and z are functions of u and v, then the partial derivative of w with respect to u would be equal to the sum of the following products. Partial derivative of w with respect to x times the partial derivative of x with respect to u, plus the partial derivative of w with respect to y times partial derivative of y with respect to u, plus partial derivative of w with respect to z times partial derivative of z with respect to u. And the partial derivative of w with respect to v would equal partial derivative of w with respect to x times partial derivative of x with respect to v, plus partial derivative of w with respect to y times partial derivative of y with respect to v, plus partial derivative of w with respect to z times partial derivative of z with respect to v. So to illustrate, given z function defined by x squared minus y times tangent of x, where x is the ratio of u to v and y is defined equal to u squared times v squared, let us determine partial derivative of z with respect to u. Now recall, as we have stated earlier, partial derivative of z with respect to u will just be equal to this sum. Partial derivative of z with respect to x times partial derivative of x with respect to u plus partial derivative of z with respect to y times partial derivative of y with respect to u. Hence, to determine the partial derivative of z with respect to u, we need to work out the following. The partial derivative of z with respect to x, which is just given by 2x minus y secant squared of x, differentiating this partially with respect to x holding y constant. And the partial derivative of z with respect to y would just be equal to negative tangent x. Again, we differentiate this with respect to y holding x constant. And then the partial derivative of x with respect to u on this basis, holding v constant, would just be equal to 1 over v, and the partial derivative of y with respect to u will be equal to 2u times v squared. And with this, we can now work out the partial derivative of z with respect to u, given by the partial derivative of z with respect to x times partial derivative of x with respect to u plus the partial derivative of z with respect to y times partial derivative of y with respect to u. But x is equal to u over v, okay? And y is equal to u squared times v squared. So if we are to express the partial derivative of z with respect to u in terms of u and v, then we will have this expression, which we can simplify to this particular form. A recap of what we had in this lesson are the following: that the concept of differentials can be extended to cover multivariable functions, that the total differential of a function in two or more variables is the sum of the differentials of the function in each of its independent variables, and that the partial derivative of several variables is determined using the chain rule.